Well, hi, folks. Welcome back here to Moonshine Radio. Today, I'd like to talk about the digital upconverter, or we call it a DUC. And today, I'd like to talk about why we use that in our 21st century transmitters and exciters. And I'm your presenter today, Dr. Moonshine Radio. Well, let's start with the need for why we would need a digital upconverter. Let's say we found some fancy dancy DAC. That's a little device there in pink. Let's say it's made by Analog Devices. It's a 14-bit DAC. It's all fancy. And I found a nice little 125 megahertz crystal that I'm going to use that as my clock for my DAC. And our goal here is we'd like to make a nice crystal clear AM radio signal at a 20 megahertz carrier. And I'd like to create the entire AM waveform all in DSP and have it come out that little DAC, and it will be the most pristine AM radio signal this side of the Mississippi River. Now, the DAC itself, frankly, is pretty dumb. I mean, it sounds like a complicated device, but really a DAC is quite simple. It's basically got a clock input and 14 pins for the 14-bit data. And basically every time that clock goes high, the DAC's going to read in those 14 bits and convert that to an analog signal. So it's pretty damn dumb. Now, without a digital upconverter, our PC would have to stream at 125 megahertz rate to satisfy that DAC, because again, the DAC is running at 125 megahertz clock. That is the clock, that is where it's set, and every time you turn that on, it runs at that clock rate day and night. And it don't care what kind of data you send it, you just better be giving it data, and every time that clock pin goes high, it's going to be reading what's on that 14-bit data line. It's that simple. So if our PC were to stream this 125 megahertz directly to the DAC, that'd be a lot of data. Our PC would probably get really hot and toasty, and with about 15 minutes in, the PC would probably blow up. So is there a better option? And it seems kind of silly, right? Because if we think about it, our AM signal, best case, on hi-fi AM signal now, probably only going to have about 15 kilohertz of bandwidth, plus or minus 7.5K. So it seems awfully wasteful to be sending this high 125 data rate for something that only has about a 15 kilohertz modulation bandwidth. So how can we put something in the middle between our PC and the DAC? And that, folks, is what the digital upconverter does. Basically, we can kind of say 15 kilohertz of data, a 50 kilohertz sample rate will be more than fine. So the best scenario is we'll have our PC stream at a 50 kilohertz sample rate, and that will go into a little FPGA chip, and that FPGA will do all the work for us, and he'll upsample the signal to 125 megahertz, and he'll also add the 20 megahertz carrier signal. So all that upconversion and the carrier insertion is being done by the digital upconverter. And then it feeds the data at a 125 megahertz rate to the DAC. The DAC is happy, it's getting the data at the rate it expects. And now the PC is going to be much cooler because it only has to work at a 50 kilohertz rate as opposed to a 125 megahertz rate. So that is the purpose and value of a digital upconverter. Now let's get into the gory details and see how we do it. Well, there it is, folks. The digital upconverter, 21st century TX hardware. If you have any kind of modern equipment, this is what's being done. From the Xilinx RFSoC chip to any other Pentec devices, all are going to incorporate this kind of design. If they don't, I would say they're a piece of shit and you shouldn't buy them because they're going to be literally pieces of garbage. So this is our digital up converter. And let's give a high level of what's going on. So the PC would stream over that IQ data rate. And remember, the IQ data rate is centered at what's called baseband. That's a fancy way of saying the data or the spectrum coming out of the computer is all centered around 0 hertz. That's what baseband is. But you might be saying, but wait a minute, I want to come out at 20 megahertz. That's where my transmitter is. Well, that's what the NCO does in the digital up converter. We'll simply set that NCO, numerically controlled oscillator, to a frequency of 20 megahertz, and now our signal coming in at 0 hertz gets up converted to 20 megahertz and then sent to the DAC, becomes a real signal. We'll apply some filter in so we got no spurs and harmonics. And we send that to our power amplifier to get it up to 50 kilowatts. And then we just send it out the antenna, and then I blast all my nonsense all over North America for you to hear. All right, let's get into the details here. So we want to have our AM signal come out at 20 megahertz. So we'll simply set the NCO to 20 megahertz. That's a simple register device, and it just does it like magic. And then you see those little up-looking arrows things with the N next to it? They need interpolation filters. So if our PC is going to be streaming data at 50 kilohertz sample rate, and we know the DAC is running at 125 megahertz, that means we need to set those interpolation filters to 125 megahertz divided by 50 kilohertz. And when you do that ratio, that is 2,500. So that's a lot less work now that the PC didn't have to do. And like I said, the PC is going to stream that AM signal at baseband, or basically centered at DC or 0 hertz. And the digital up converter is going to upsample the 50 kilohertz bandwidth to a 125 megahertz sample rate, and it will add the 20 megahertz by the NCO. And you can see we can change the frequency to be 10 megahertz, 5 megahertz, basically anything from 0 to 125 megahertz divided by 2. We can put our AM signal, and simply by changing that NCO, we can be pretty much anywhere from 0 hertz up to about maybe 50 megahertz or so. No tuning capacitors, no fumbling with inductors. You just set the register to whatever frequency and it comes out of that DAC. And all that magic is being done by the digital up converter. Now we're finally starting to see ham radio gear using this. All those bloated and overpriced Anons and Flex radios, I think are starting to use all this. But hopefully this explains to all those out there why we have digital up converters and the need for them to basically take the bandwidth and put that on the FPGA as opposed to our computer. And that's the purpose of the digital up converter. Now, for those of you that think I'm blowing smoke and I don't know what I'm talking about, well, here we go. Here's a modern receiver, or sorry, modern transmitter, I should say. And this whole thing is on a PMC card, no bigger than a couple pack of matches, folks. And if you look carefully here, I don't see no inductors, I don't see no capacitors. All the DSP and signal generation, folks, is being done by digital logic circuits. You see, the digital logic these days, it can run at clocks up at 1.25 gigahertz. So if I'm trying to make an RF signal anywhere around there, I'd be silly to do it analog. We can just do it here. And you can see up there, you got 4 DACs, right? And they're all 16 bits. and they're all running at a clock of 1.25 gig. Now that FPGA, it ain't going to be streaming 1.25 gig. That's what the digital upconverter will do. It digitally upconverts that data for us. So the data back at the PCI Express, or wherever you're going to stream the data in really, can be a much lower rate. And we let the FPGA and these digital upconverters do all the work for us. So I just wanted to show you guys that this isn't some imaginary thing. This really does exist in modern transmitters, exciters, etc. Well, that's all for now. Hopefully you folks out there learned something today about the digital upconverter. Alright, that's the end. And the next few videos here, we'll use our little red pitaya with Pavel Demin's firmware, and we'll actually institute a digital upconverter. And basically what that firmware will allow us to do is we can stream IQ data from the computer by using GNU Radio to the red pitaya, and we can output RF signals. And we will show how we can make a 21st century SDR exciter. And this exciter will be able to do amplitude modulation, frequency modulation, single sideband modulation, any kind of digital modulation, or waterfall images in the SDR waterfall. So stay tuned and we'll get into all those details. Bye for now.